right, in our previous video, for the HPS side, the hardcore processor side of our DE10 standard, we went through setting up all the tools in Windows and compiling a basic Hello World application that we then ran on embedded Linux on the DE10 on the ARM hardcore processor side. Today we're going to be expanding on that video. We're going to create our own custom HPS system, and in that system we'll add a Avalon PIO core to control the LEDs on the DE10, and then we'll write an application to actually do something where we blink the LEDs, or haven't decided quite what we're going to write yet, but we'll figure out something kind of cool. So let's get started. We're going to do this a little bit differently than we have been with our other systems. Thoracic actually gives us a system builder application, and if you're doing HPS stuff, this application actually makes a lot of sense because we can't do our little trick that we've been doing with the NIOS where we name it the same as the top level and everything just kind of magically works out. So we're going to go ahead and fire up that application, and we will go ahead and create our top level. So we'll call this HPS Hello PIO. And then we're just going to uncheck most all of these things. We only need a few things, right? We need the clock, we need the LEDs, and we need the HPS system. That's all we really need. So I'm going to go ahead and hit generate on this, and then let's make sure I'm in the right folder, which I am not. Let's go down to my video demo folder, and I've got a folder already created called HPS Hello PIO, and we will throw this project into there. And there we go. We can now close that, and we can open up our folder over here. Here we've created our HPS Hello PIO, and we'll go ahead and open up that QPF file. Okay, Quartus finally finished opening all the way, and the graphics are back to normal. Now if we look at this top level, we can clean some of this up. We don't need all of this, but basically it gives us a top level for everything we selected in that system builder. We got an area for registers and wires if we need it, and we got our area for our structural stuff that we're going to bring in. We only need one clock for this, so I can get rid of the other 3 clocks. I don't need this top pin. I do need all the DDR3 stuff. I do need all of the Ethernet stuff. I don't need the flash or G-sensor or the I2C or the keys or the LCM or the onboard LED or the LTC. I can get rid of all of those pins. But I do need the SD card. I don't need the SPIM. I do need the UART, and I do need the USB. So those are the things we need. So now that we have that, it's time to go ahead and fire up our platform designer and get to designing our system. All right, we now have platform designer open. Let's go ahead, and the first thing we're going to need is our HPS processor. So we'll just type in HPS, and there it is, our Area 5 Cyclone 5 hardcore hard processor system. So we will double click on that. All right, as we can see, there are a ton of things that we need to configure. First and foremost, we're going to turn most of these FPGA interfaces off. I don't need the standby and event signals, so I can uncheck those. You'll notice that the platform designer is a little bit slow. Every time you make a change, it has to verify that that change isn't going to break anything. We're not going to use the FPGA to HPS interface or the FPGA to HPS to FPGA interface. We are going to use the lightweight HPS to FPGA interface, so we'll leave that one. We don't need the 64 megs of SD RAM that are on the FPGA side, so we can get rid of that. Not going to change anything with the resets or any of this other stuff here down below. So that's that piece. Next, on our peripheral pins, this is where we set what peripherals we're going to use. And we're going to use the Ethernet controller. So we're going to go down here to EMAC 1, and we're going to set that to be HPS IO set 0. And once that comes in, it should change our mode, there it is, to the RGM-II, which is correct. We're not using the NAND or the Quad SPI. We are going to use the SD controller, so we need to bring that one in. And on this one, I believe it's going to default to 1 bit of data. We need it to be 4 bits of data. We do need the USB controller. So USB pin 1, we're going to set to that set 0 as well. And this one should default to what we need, which is SDR with PHY clock output mode. We're not using SPI. We are going to use our UART. So set UART pin 0 to our set 0. And then I believe it's going to default to flow control, and we don't want flow control, so we'll set it for no flow control. Don't need pin 1, don't need the I2C, don't need the CAN controller, don't need the trace port. There is one other thing we got to do, and we need to export GPIO pin 35. This is needed by the Ethernet controller. If you look through the data sheet, you'll find that out. So we'll just click on GPIO 35, and that will basically kind of bold up our pin here saying that it's being exported. So that is our FPGA interfaces and our peripheral pins. Next are our clocks, and we really don't need to change anything to our clocks. Our inputs are fine, 25 and 25. And our outputs should not change as well. So we're not going to change anything in the clocks. The next area where we do have to make lots of changes is the SD-RAM. So we need to set this up for using our DDR3. We have 1 gig of DDR3 RAM on the DE10 standard, and we've got a lot of parameters we need to change. First and foremost is our memory frequency is 400 megahertz. And once that change goes through, I'll be able to change the PLL reference clock, and that should be 25 megahertz. Supply voltage should be 1.5. Everything else should stay the same. There we go. You'll notice, like I said, there's a little bit of lag. It's going to check a bunch of things before we move on. Next, under our memory parameters, the first thing we got to change is this is using Micron memory. It's not JEDEC, it's Micron. So we'll swap it over to Micron. And then we also need to change our speed grade to 800 megahertz. And then once that is done, we need to change the total interface width to 32. That should automatically change our DQS groups to 4 when that applies. There we go. And then our the chip select depth and the number of clocks are both 1. Our rows are 15. Our columns are going to be 10. And our bank address width is 3. We're not going to make any other changes except for down here where we've got our cast latency. That should go to an 11. And then our ODT, RTT nominal value, that should go to RZQ6, manual normal, and this memory write cast latency should go to a 7. So there we go on that one. The next big one is our timing parameters, and there's a ton of things we got to change here. So let's get started at the top here. The first one should go to 190. That next one, instead of 250, is going to be a 140. And then instead of a 50, we're going to have a 30. Just waiting for that little red squiggle so I know it applies, so I can go to the next one. And then our last base is going to be 65. And then our DQ, SQ will be 125 instead of 120. So that's going to go to a 5. The next one is actually right at 0.38. But this next one should be 255. And the next one after that is actually correct at 0.25. But then the following one should be 0.4. And then the next two are both 0.2, so that's right. And then this one goes to 500. And then our clock, our number of cycles is 4. And then our RAS is 35. The next two numbers, the RCD and the RP, those are both 13.75. So we'll change both of those. Our FI is 7.8. And then our RF cab, this is a big change. This goes to 260. Our right should be 15. And our WTR should go to a 4. Our FAW should go to a 45. And then the last two should both be 7.5s. All right, the last thing we got to set is our board settings. We're going to leave the use default and the use default, but we do need to change our board SKUs. So this is 0.03, excuse me. And the next one will be 0.02. Minimum delay is 0.06. Maximum delay is 0.12. Our DQS group is 0.01. And our maximum skew between DQS groups is 0.06. DQ and DQS, the difference is 0.05. That next one is in fact 0.02, and the last one is 0.01. So that is all of our parameters set. I can go ahead and hit finish here. And then we just need to wire it up. So there's not a lot to wire on this one. Our H2F reset goes up to our reset, and then our clock comes down to our AXI clock. As soon as I can get that wired, there we go. So the next thing I need is my PIO core. So we'll go grab our PIO core, and we will make this 10 bits of output. And I'm just going to rename this the LEDs. I'm going to export my LEDs. And then we need to wire up clock, and we need to wire up reset. And now notice we have an Avalon memory map slave, and the only place we can wire that up is to the lightweight AXI master. Well, the AXI bus and the Avalon bus are two different buses. The nice thing about this is the fact that Platform Designer will throw in whatever kind of bridge it needs in order to talk to all these devices for us. We could manually add them in as well, but I found it best just to let Platform Designer do it for us. And I missed the clock right there for some reason. So let's get the clock wired up, and that should be our system that we want to make, right? We've got basically simply a clock, our processor system, and our PIO cores. So with that, we can go ahead and do a file save. We'll just call this HPS hello PIO. And as soon as that save is completed, there we go. We can now hit that Generate HDL button, and I'm just going to take the defaults here. All right, our HDL is generated. We got to do one more thing before we leave Platform Designer. We're going to go up here to Generate, and we're going to show our instantiation template. This is what we're going to cut and paste into that top level, and it's basically just a template on how we instantiate our HPS system. So I'm just going to hit copy there, go ahead and close, and when I hit finish, Quartus, like normal, is going to say, hey, you created some IP, you should bring that in. We will do that in just a second, but first I want to paste in my instantiation template. Then we can go up here and bring in our quip file, which brings in our IP that we just made. So we'll go ahead and hit OK there. All right, now we are ready to go ahead and start wiring up our top level. Basically, we just got to copy these names down into these names for our map, and we're good to go. And through the magic of video editing, we are done with that tedious task. So we've mapped all of the names from here down to here. So there's my clock. Here's all of my DDR3. My Ethernet, the SD card, my USB, the UART. This one right here goes to, remember we exported pin GPIO pin 35. That is the Ethernet interrupt line that has to be hooked up. And then of course our LEDs. Now I've already fixed my project, but I'll show you how. The next step would be to do a full compile, and it's kind of a quirk, a bug I think in Quartus, but you have to do a full compile and have it fail before you can actually fix things. Once that full compile fails, you go up to Tools and you go to Tickle scripts or TCL scripts. And there's a number of Tickle scripts that get generated. The two we care about are the parameters and the assignments. So you'll just click on the parameters first and hit run. And then you'll click on the assignments and hit run. And that one will take a little bit of time. All right, that one's finished. And then when you're done, you would do another full compile. I've already done that. So at this point, what I am going to do is program the FPGA. So we can bring up our programmer, and I'm going to bring up our camera as well so we can watch it being programmed, and I'm just going to go ahead and hit start. And of course right now nothing's going to happen because we haven't actually written any code yet, right? But there we go, everything went off, we've programmed our FPGA, so now we're just kind of waiting on some code. Now, to write the code, the first thing you have to do is generate this HPS_0 file, and the way we do that is in the SOC EDS shell. Let me scroll up here. Looks like I might not have it in here. Okay, so I'll just go ahead and regenerate it really quickly. Basically what you have to do is parse your SOPC info file. Luckily, the SOC EDS tools give us a tool to do that. So basically, we just got to run SOPC-create. That should be enough to hit tab. So it's SOPC-create-header-files. And then you got to point to where your .sopc info file is. And then we want to produce a single file for our HPS_0.h. And our module that we are using is our HPS_0, which is what we named it in Platform Designer. So we'll go ahead and run that utility. That will parse our SOPC info file, and it will create our header file. So now if we look, we have our header file. I'm just going to go ahead and do a make clean here really quick. Now I've already written some code, pre-written some code for us. So we're just going to hop over to Notepad++, and it's going to tell me that yes, indeed, the HPS file changed. Meg file is basically the same one we used last time. You just got to change your target and your .o files each time. But let's take a look at our code. So we need a number of includes. Standard IO, that gets us printf and stuff. We need unistandard.h for some other calls. We need file control because we're going to use some file descriptors. Memory manager, we need that. And then we need some some includes from Altera. We need hardware lib. SoCal, we need our HPS, we need the Altera GPIO libraries, and then of course we need our generated HPS suite. The next thing we got to do is make some defines. We need to define the address of where our hardware registers are. Luckily, Altera gives us a define where those are. It's the Altera STM offset. And we also need to define how big they are. We're going to map the entire range, which is 0x0400. 0000. And then we got to create a mask, which is just our span -1. Next, we need a few variables, right? So we're going to create a return val. We need a file descriptor. And we need a couple pointers for our virtual base and our LED address. So first step is to try and open devmem into our file descriptor. We're going to open it for read-write and for sync. And of course, if that fails, we're going to just error out of the program. If that succeeded, then what we have to do is do a virtual memory map. So that's using the mmap function. And basically, we're going to set that to our virtual base address of where all of our stuff is. Parameters, first one's null, then our span. We're going to do attributes of protected read and a protected write. This is shared. We got to give it our file descriptor and then our base address where things start. And of course, we're going to check if that failed. We can't do anything, so we'll just close our file descriptor and get out of here. If that worked, then we need to calculate our LED base address. So we'll calculate that. That's our virtual base plus our offset of where the lightweight FPGA HPS to FPGA bridge is, the slave controller. And then beyond that is where our LED's base is. We got our LED's base out of our HPS 0. Our LED's base happens to be 0, 0 because we didn't have anything else in there, so that's where it started. And then of course we need to AND that with our mask for our hardware regs. And then we're simply going to turn all the LEDs on. We're going to wait 1 second. We're going to turn all of them off. And then we're going to clean ourselves up. We're going to unmap our virtual base, make sure that didn't fail, close our file descriptor, and then return whether we were successful or failed. So let's go ahead and open up our shell again, and we will just do a make. That should build our system. Let's go ahead and do a listing, and there indeed is our executable. So now we need to come over here, and since we just programmed the FPGA, I'm going to bring the camera back up. We just programmed the FPGA, right? So we actually need to do a soft reset, a warm reset on our board. I'm going to go ahead. It's this first of the user buttons right here. I know it's hard to see. It's that one. So tiny. That's going to do a warm reset on the hardcore processors, which will reboot our Linux system and take effect with the new hardware that we put into the FPGA. So there we go. We can now log in as root, and we need to run our UD HCPC, which will run our DHCP client. All right, then we can do an IF config. And here we go. We can now SCP our HPS hello PIO to root at 10.101.131.166. And that's going in the /home/root folder. Yes, now you want to do that. So there we go. We've now copied that over. Let's bring our camera back up. Now if we do a listing over here, we see our file. And we'll go ahead and run that. There they're on, there they're off, right? So our program works. We've now written a simple program that can talk to a custom HPS system that we've made that's just got that PIO core in it. The fact that Platform Designer put in all the bridges that were necessary, and I can now do a virtual memory map to that location in memory on the Linux side, and I can talk to those GPIOs and do what we need to do. So that will conclude our demo, and we'll be having some more videos coming your way.